Good morning. Now we are going to discuss Unit 3, Deflection of Beams. And our first topic in third unit, Elastic Curve and Governing Differential Equation. Before going to this topic, we have to know what is meant by beam and what is deflection. In second unit, we are clearly studied different types of beams, such as simply supported beam, cantilever beam, fixed beam, continuous beam, etc. And also we have to know how to calculate CFOs and bending moment, and how to calculate and draw the CFOs and bending moment diagram in second unit. In third unit, we are going to study what is meant by deflection and what is meant by slope, and how will we calculate this slope and deflection of a beam, etc. The following assumptions are undertaken in order to derive the differential equation of elastic curve. In order to find out this elastic curve or governing differential equation, some assumptions are made. First one is stress is proportional to strain. We know that Hooke's law is applicable for up to the proportional limit only. Beyond that, we cannot apply this Hooke's law. Similarly, in order to calculate the deflection of beams, we are assumed that the stress is proportional to strain within the elastic limit only. Beyond the elastic limit, we cannot calculate the slope and deflection. And the second one, the curvature is always small. When the external load is acting on the beam, some amount of curvature is always produced. That amount of curvature is very small quantity, hence we can neglect this curvature. And third one, any deflection resulting from the shear deformation of the material or shear stress is rejected. Purely we are calculating the slope and deflection with respect to tensile and compressive stresses only. Due to shear deformation, we cannot calculate the deflection derivation. Consider a beam AB which is initially straight and horizontal. The beam is originally horizontal position whose length is AB. After the application of loading, the beam deflects and tends to the position A dash B dash. In order to express the deflected shape of the beam, we can express this deflection shape by means of using x and y coordinates. Here, x coordinate is used to describe the length of the beam, and also y coordinate is used to identify the deflection of the beam. Once the external load is acting on the beam, some amount of lateral deflection is occurring in the beam. It is in the downward direction. With respect to the horizontal position, how much amount of deflection is occurred in the beam, that is the matter. In order to calculate that particular deflection, we have to use some special equations. Further, let us consider a small elemental strip ds. Initially, the beam is in AB position. In that particular position, after the application of load, it tends to the final position A dash B dash. In the final position, we are considering a small elemental strip. It's an imaginary strip whose dimension is ds in the deflected beam. At the end of this element, let us construct the normal which intersects the point 0, denoting the angle between these two normal. It's a graph. We are going to construct a graph in which it deflects the total amount of deflection, and also the slope is identified in this graph. For the deflected shape of the beam, the slope I at any point is defined. In that particular graph, we have a small angle of intersection which is denoted by the letter small I. In order to calculate this slope, we can use the formula tan I is equal to dy by dx, where dy and dx are the coordinates in the y and x direction respectively. We know that tan theta is equal to opposite divided by hypotenuse. Tan I is equal to dy by dx. For the smaller values of tan I, we can write directly it is I. Hence the equation becomes I is equal to dy by dx. Further, in order to calculate the elemental strip ds, we can write ds is equal to radius of curvature r into di, where di is the small slope portion found intermediate between these two lines. ds is equal to r into di, hence we can written ds is equal to dx. For the smaller amount, I is equal to tan I, so it is this small curvature becomes ds is equal to dx is equal to r into di, or we can rewritten this equation as di by dx is equal to 1 by r. By substituting this value in the above equation, we can get instead of I, we can get the value d by dx into dy by dx is equal to 1 by r. Instead of I, we are substituting this value d by dx of dy by dx, which is equal to 1 by r. So the equation becomes d square y by dx square, which is equal to 1 by r. From the simple bending theory, in second unit we have already studied the simple bending equation. M by I is equal to sigma by y is equal to E by r. From this relation we can written M by I is equal to E by r. By reducing this equation, M is equal to EI divided by r. Or instead of I, we can write M is equal to EI into 1 by r, we can write d square y by dx square. In this equation, M is equal to 1 by r into EI. Instead of 1 by r, we can write d square y by dx square. Hence the equation becomes M is equal to EI into d square y by dx square. This differential equation of the elastic line for a beam subjected to bending in the plane of symmetry, its solution y is equal to f of x defines the slope of the elastic line. So this M is equal to EI into d square y by dx square. This equation is known as governing differential equation, or in order to find the bending moment of the beam, we can use M is equal to EI into d square y by dx square, where y is the deflection of the beam. Once we know the value of deflection, we can easily identify the bending moment and also shear force. Then what is the relationship between the shear force and bending moment? Slope is equal to dy by dx, where y is the deflection of the beam. If we want to find out the slope, means once we differentiate the slope with respect to dx, then we get the value of slope. Similarly, for calculating the bending moment, we can double integrate the deflection equation, that is bending moment is equal to EI into d square y by dx square. For finding the shear force value, it is given by EI into d cube y divided by dx cube. Third order derivatives gives the shear force value. For finding the load value and load distribution, we can use the formula of EI into d power 4 y divided by dx power 4. It is nothing but once we differentiate the slope, means deflection means we can get the value of slope, and again we integrating, we can get the value of bending moment. Again integrating the same equation, we can get the value of shear force. Finally, integrating the deflection value with fourth derivatives, we can get the value of load distribution. Methods for finding the deflection. Generally, the following methods are used to finding the slope and the deflection of a beam. So, in our third unit, we are going to discuss the following four methods. First one is direct integration method or double integration method. In this direct or double integration method, by using the direct formulas, we can easily substitute and get the values of slope and deflection of the beam based upon the nature of forces acting on the beam and types of the support conditions. So what are the methods available means, first one direct or double integration method, second one is Macaulay's method, third one is moment area method, and the fourth one is conjugate beam method. These four methods are briefly discussed by this third unit. We will see one by one another. The first one, direct integration method. In order to use this direct integration method, we can use the governing differential equation, which is already we have derived in the previous step. M is equal to EI into d square y by dx square, or we can rewrite as M by EI, which is equal to d square y by dx square. The second order derivative of the slope with respect to the direction gives the bending moment of the particular beam with respect to its flexural rigidity. Dy by dx, which is equal to integration M by EI into dx plus A. Partial derivatives of this d square y by dx square, which gives integration M by EI into dx plus A, where A is the constant of integration. Again, integrating the same equation, we can get integration of dy by dx, which is equal to y, which is equal to again in the right hand side, integration of M by EI into dx plus A. We got double integration of M by Ex into dx plus Ax plus b, where A and b are the first and second order constant of integration. By applying these boundary conditions, we can get the values of A and b, and finally we can get the values of slope and deflection. So some key points to remember in this topic: simple bending equation, which is nothing but M by I is equal to sigma by y is equal to E by R, where M is the bending moment in kilonewton meter, I is the moment of inertia of the beam in meter power 4 or mm power 4, E is the Young's modulus of the beam in Newton per mm square, R is the radius of curvature of the beam, and similarly sigma is the bending stress. When the bending load is acting on the beam, some amount of bending stress is generated. That bending stress is denoted by the letter sigma, so it is in Newton per mm square, and y is the deflection of the beam in mm. In general cases, we are normally calculated deflection in mm or centimeter, and the governing differential equation is given by M is equal to EI into d square y by dx square, where d square y by dx square is equal to 1 by r. Instead of 1 by r, we have to substitute this d square y by dx square, and the formula becomes M is equal to EI into d square y by dx square, and slope is denoted by the letter dy by dx, and deflection is denoted by the letter y.